In this part of the video, we're going to explore part B questions. In the first question, we're given an operator defined over a field, and we're given the characteristic polynomial. So first thing that I look at when I'm given the characteristic polynomial, this tells me that T is a linear operator on V, and that the dimension of V equals 2. Because it's a quadratic. Whatever the dimension of the characteristic polynomial is, that is the dimension of the vector space V. From here, it asks for us to define a field from class for which T has one characteristic value. What this means is that I am able to factor. So I can factor. And 2, I have one repeated root. I have one repeated root and I can factor. So looking at this and I'm going, okay, how can I do this? How can I do this? Um, when looking at it, I see a 3 in here. So because I see a 3, I know it's not Z mod 2. I know it's not Z mod 3. Z mod 5, maybe. So I can immediately go to Z mod 5. And what I'm going to do is I'm going to look in Z mod 5 to see if I can plug something in and get 0. And in Z mod 5, if I plug in a 1, this equals 1 plus 3 plus 1, which equals 0, or 5, which equals 0, because it's Z mod 5. So I can divide by x plus 4. Remember, this is x minus 1, but it's the additive inverse of minus 1, which is 4. Now, x squared plus 3x plus 1. X goes into x one time. I subtract by x squared plus 4x, giving me 0. And now I'm adding the additive inverse of 4, which is 1. So this is 4x plus 1. So this goes x times, and now I'm going to add 4 to it to give me 4 minus 4x plus, and now 4 plus 4 is 3, or 4 times 4 is 16, which is 1 if we mod out, and when we subtract, we get 0. So it becomes x plus 4 times x plus 4. Now, if I want to know what the characteristic is, it's the roots. And the roots of the expression, this is x minus 4, or 1. So my roots are 1. Even though the factors are x plus 4, my roots would be 1. But it does work, meaning that if f equals z mod 5, then there is a repeated, or then there is one characteristic value. Okay. Now, here, suppose T is not diagonalizable, provide the rational form of T. So this is really an extension of this field that we're using. So here, I know that my characteristic polynomial, f of x, has now become x plus 4 times x plus 4, or x plus 4 squared. Now, with it being x plus 4 squared, I know that this polynomial here is not going to be, with it not being diagonalizable, that means that p of x also equals x plus 4 squared. Meaning that in the rational form is just a singular block matrix, a 2 by 2 block matrix with p of x equaling f of x equaling this polynomial here. So it's going to be 0, 1, and now it's the additive inverse of 3 and the additive inverse of 1 coming from these polynomials. But remember, we exist in Z mod 5, so I'm not allowed -1. It has to be the additive inverse of -1, which is 4, and the additive inverse of 3, which is 2. So this is my rational form. Okay. Again, I'm showing you the workings through it. I'm not providing a beautiful, detailed solution. Okay. We'd expect it to be a little bit more organized, but this helps you understand the thought process I was going through. Now, suppose that it's defined over the real numbers. Y is t, and here, y is t diagonalizable. Well, if we look at this expression, we got, if I'm looking at x squared plus 3x plus 1, and I look at I'm looking at -3 plus or minus the square root of 9 minus 4 over 2. Lambda equals -3 plus or minus the root of 5 over 2. Here, I'm looking at it, I'm going, I have two roots. The discriminant is non-zero. I have two distinct roots. Thus, f of x equals x minus -3 plus root 5 over 2, x minus -3 minus root 5 over 2. Therefore, the characteristic polynomial is a product of distinct linear factors. Thus, t is diagonalizable. This is one of the theories we could use. Another theory we could use is the minimal polynomial has to equal the characteristic polynomial, and the minimal polynomials are product distinct linear factors. You could show that the eigenvectors, there has to be an eigenvector for each eigenvalue. So there has to be a basis of eigenvectors. There's a bunch of different arguments you can make. As long as you have a valid argument, that's all that we're looking for. B2, here what we're doing, what's happening is we're given a dependence relation. And here when I'm looking at the dependence relation, I'm looking for any information we have about the operator. Remember, I really, really care about the dimension of V because that tells me the size of my matrix representation. That's a big deal for me, especially when we're looking at our Jordan canonical forms and our rational canonical forms. Okay? Here what it's saying is that we have dependence relations and we're looking for operators that satisfy the dependence relation that are not diagonalizable. So if a non-diagonalizable operator exists that satisfies the dependence relation, define the Jordan canonical form of that operator. If all operators must be diagonalizable, pick one of the possible minimal polynomials, define the corresponding rational form for the operator. Okay. So here, when I'm looking at this, I'm going, okay, one could be non-diagonalizable, one could be diagonalizable. And with dependence relations, I really care about taking it and factoring it and creating a polynomial that represents the dependence relation. So this means that t squared minus 2t plus I equals 0. If f of x equals x squared minus 2x plus 1, then f of t equals 0. Factoring this, I get x minus 1 squared. Okay. Down here, I'm looking at, I'm going, okay, I got t squared minus t equals 0. If f of x equals x squared minus x, then f of t equals 0. And this is x minus 1. Now, The key with this is that the minimal polynomial, the min poly, must divide f. Okay, so here, the minimal poly could be x minus 1 or x minus 1 squared. If it's x minus 1 squared, we are not diagonalizable. So this one here could, or a non-diagonalizable operator exists. Okay. Now, if a non-diagonalizable operator exists, define the Jordan form of the operator. So what I need to do is I need to define the Jordan form of this particular operator. Well, I know that its minimum polynomial is going to be x minus 2 squared. So that's going to be the P1. And what I'm going to do is I'm going to take the characteristic polynomial, which has to have the same roots. So it's x minus 2. And it's going to be cubed because my dimension is 3. And now what I'm going to do is I'm going to do the rational decomposition followed by the primary decomposition like we were doing before, given these two constraints, the characteristic polynomial and the minimal polynomial. Well, here, if I look at it and I break it up into the two blocks, I've got P and W. Well, the characteristic polynomial FW equals x minus 2 cubed over x minus 2 squared, which equals x minus 2. And the minimal polynomial has to have the same root, so it's also x minus 2. So what I've got is I've got P1 is x minus 2 squared, and P2 is x minus 2. And I build the rational form for that. Well, I need to expand x minus 2 squared to x squared minus 4x minus 4. Or x minus, sorry, this should be 1. Should be 1s everywhere. 1, 1, 1, 1, 1. So it's x squared minus 2x plus 1. So the companion matrix for that would be 0. It's a 2 by 2 companion matrix. So 0, 1 in the first column. The next column is going to be negative, negative 2, so 2, and negative 1. And then the last one is a 1 by 1 companion matrix for the expression x minus 1. So this is my rational form. Now here, my dependence relation is a product of linear factors, which means my minimum poly is going to be x minus 1, or x times x minus 1. Okay? All of these are products of distinct linear factors. Thus, always diagonalizable. So we're always going to be diagonalizable. So now what we have to do is we have to pick one of the minimal polynomials and define the corresponding rational form. So what I'm going to do is I'm just going to try to pick one that's easy. My minimal polynomial is x. This implies that f of x, my characteristic polynomial, is going to be x cubed. And when I break it up, it's going to be x p1 of x equals x p2 of x equals x, and p3 of x equals x. So my rational form is going to be 0, 0, 0, with zeros everywhere else. I get the 0 matrix. Now, what you might have also noticed, this is a projection, which means our matrix is always going to have the form 1s, with zeros. The ones, there could be no ones, there could be 1 1, there could be 2 1s, there could be 3 1s. So really what we could have is we could have one of the following. Those are the possible rational forms. And turns out they're also Jordan canonical forms. In B3, what we have is we're given a characteristic polynomial and a rational polynomial, and we're asked to break it down to figure out all the possible rational forms. So here what we're going to do is we're going to start by doing the first breakup into our two groups. And from here, I've got P1 of x equals x minus 2, x minus 3 squared. And this is W1. Now, f of W1 of x is going to equal x minus 2 squared, x minus 3 to the 4 over x minus 2, x minus 3 squared. This is going to equal x minus 2, x minus 3 squared. From here, I've got two options for P2 of x. This is option 1. This is option 2. Option 1 is x minus 2, x minus 3. And option 2 is x minus 2, x minus 3 squared. Now, if we go with this option 2, then because my characteristic is a 6 by 6, I still have to break it up again. So I get another W2. W2, if I look at f of W2, this equals x minus 2, x minus 3 squared over x minus 2, x minus 3, which equals x minus 3. And P3 of x equals x minus 3. Whereas here, as f of W1 equals P2, we're done. Okay? So at this point, we are finished. So now I have these two different pieces. And what I'm going to do is I'm going to label it option 1, option 2. And I'm just going to, for my sake, just write out what my P1 of x is. And this is x minus 2, x minus 3 squared. And P2 is x minus 2, x minus 3, and P3, x minus 3, right? And then what I'm going to do is I'm going to expand these. So here I'm looking at this and expanding. It's x squared minus 5x plus 6. And now I've got to multiply x squared minus 5x plus 6 one more time. So I'm going to do x squared, x cubed minus 5x squared plus 6x minus 3x squared plus 15x minus 18, x cubed minus 8x squared plus 21x minus 18. And I'm just going to hope that that's correct. Minus 3 minus 8x squared plus 21x minus 18. And option 2, P1 of x equals P2 of x equals this expression, x cubed minus 3 or 8x squared plus 21x minus 18. And from here, we get our two rational forms. So here we have 3 blocks. First one is a 3 by 3, where the coefficients are 8 minus 21, 18. Then we have a 2 by 2, which have coefficients 5 and minus 6. We have a 1 by 1, which has coefficients 3. And my second rational form has 2 blocks, the two blocks are the exact same, 0, 1, 0, 0, 0, 1, 8 minus 21, 18, 0, 1, 0, 0, 0, 1, 8 minus 21, 18. And these are my Jordan blocks, and it might help when defining a rational form to block it off in this way. Okay. Now it's saying, further suppose that the rational form is a direct sum of two companion matrices. So because it's two companion matrices, it has to be option 2. So in part B, it has to be option 2, and I want the rational form. So what I'm going to do is I'm going to take the Jordan canonical, or the rational, the cyclic decomposition, I'm going to further decompose it. So I've got x minus 2, x minus 3 squared. This is P1, and P2 is x minus 2, x minus 3 squared. This breaks up into P11 of x equals x minus 2, P12 of x equals x minus 3 squared, P21 of x equals x minus 2, and P22 of x equals x minus 3 squared. So when I break this up, I've got 4 things. This is a 1 by 1 Jordan block, a 2 by 2, a 1 by 1, and a 2 by 2. So it's going to be 2, 3, 1, 0, 3, 2, 3, 1, 0, 3. And that is my Jordan canonical form. Now you can reorder it if you would like, but this is a perfectly valid Jordan canonical form.